So, a very good morning to all of our attendees. My name is Vidish, and on behalf of Midas IT, I'd like to extend a very warm welcome to each and every one of you to today's webinar session on cable stayed bridges modeling and analysis. So, before beginning the session, I'd just like to do a quick sound and video check just to make sure that everyone online can hear my voice and whether or not the presentation slide is visible to you on your screens. Okay, so there doesn't seem to be any problems. So we'll begin the web session now. Just a few things I'd like to mention before starting out with the web session. For our first-time viewers, if this is your first time using the GoToWebinar software, you can hide the dialog box by clicking on the red arrow so that you will have more focus on the video itself. You can type your questions. If you have any questions at any point during the web session, you can type them into the chat box, and I will respond to all of your queries immediately after the webinar is over. Okay, so with that, let's get this session underway. So these are the contents of today's presentation. First and foremost, I'll talk briefly about our company, Midas IT, and our software, Midas Civil. Then we will jump right into the presentation, wherein I will discuss modeling and analysis philosophies associated with the cable stayed bridges. And towards the end, I will also briefly discuss second and third order effects in cable bridges and how they compare with each other. So first up, about Midas IT. We've been developing programs since 1989, when initially we were formed as an offshoot of the POSCO group, and commercially we have been doing so since 96. We were incorporated in 2001, and currently we are headquartered in Seoul, South Korea, and have offices in China, Japan, Singapore, London, India, United States as well, and we are ever expanding. We are among the largest CAE software developers in the world, with a proven reliability of over 5,000 project applications, following an intensive quality control system, together with our analyses having been verified by various institutions the world over. Talking about our product, Midas Civil. Well, first of all, for those of you who are not aware of the program, Midas Civil is a finite element analysis package that is specialized for both 2D and 3D finite element analysis. It is at once a general purpose as well as a specialized purpose tool, in that it can be used by both the structural as well as the geotechnical engineers. Although it is geared towards the bridge engineer, it is also capable of handling other civil structures like underground structures like basements, buildings, plants, tunnels, and dams. Of course, when it comes to design, it is more geared towards the bridge engineers. And speaking of bridges, Midas Civil can easily handle the conventional bridge types, so bridges like culverts, slab and girder bridges, integral bridges, to the more complex stage segmental bridges. So for example, bridges constructed using the balanced cantilever method, incremental launching method, the full staging method, and others. And the software can also handle the most complex cable bridges, so cable stayed bridges, suspension, and extra dose bridges. Let's now get into the crux of today's presentation. First, let me talk about the modeling philosophy that is commonly associated with cable stayed bridges. So first and foremost, I'll talk about initial sizing for cable stayed bridges. Now, aside from loadings, the pylon and deck geometry and the orientation are usually driven not by engineering decision but more by cost and aesthetics. Engineering decisions usually come into play first and foremost when we are proportioning the spans, particularly the ratio between the side span and the main span. In these cases, backstay forces are a critical determining factor, especially because backstay forces are maximum when the live load is on the main span and they are at their minimum when it is on the side spans. And because backstay forces usually get the largest stress variation among all the cables, they have to be dimensioned in such a way that these stress variations are kept safely below their fatigue strength. So a lot of research has gone into this this proportioning over the years. One such research by Jimsing and Georgakis in 2011 is what I'm showing to you today. On this graph before you, you can see the ratio between the side span and the main span, which has been plotted on the vertical axis, and the ratio between the live load and the dead load, which is plotted on the horizontal axis, and how basically the ratio compares to the ratio of the dead loads. The value of zeta that you see just above the curves is essentially the ratio between the minimum possible backstay force to the maximum possible backstay force experienced by any particular bridge. Progressing a little bit further, let me now talk about the modeling methods for software-aided modeling of cable stayed bridges. So we have three major modeling methods that are utilized in the world today: spine beam or line beam models, multi-scale models, and meshed finite element models. So let's talk about these one by one. First up, the line beam or the spine beam model. This is of course the most common modeling method around the world today, not only for cable bridges but for nearly any kind of bridge. The bridge is basically modeled using beam, truss elements and links which represent the bearing or support conditions. The deck section can be modeled simply by using the equivalent section properties like moment of inertia, shear area, and so on. And therefore, it is usually a very preferred method of modeling, particularly for an initial estimation or an initial analysis. Let me talk a little bit about modeling of cables. Now, as all of us already know, cables are highly nonlinear structures. The stiffness of a cable element is directly dependent upon the amount of axial force that it is carrying. So, in normal linear static analysis, this nonlinear effect of the axial force also has to be considered, and to undertake that, the Ernst formula is commonly utilized. So in Midas Civil as well, the Ernst formula is implemented via the use of the cable element, which can automatically consider the effect of sag and modify the stiffness of the equivalent elements. This graph released by Walter and others and also by Fresnay in 1999 investigates the variation in relative stiffness of a cable element directly in relation to the length to its length at different axial stresses. So as you can see, for the same horizontal length LH, the higher the amount of axial stress, the more is the relative stiffness. So particularly in cases where cable length is very, very long, the effect of the variation, or rather the difference between the stresses from the material stiffness to the actual stiffness, can be quite a lot and definitely has to be considered. Coming now to multi-scale modeling. Now, multi-scale modeling essentially means that the model is composed of a combination of simple line models or beam models, beam elements, plate or shell elements, and solid elements. So the major use of this kind of a model is simply to capture more accurately the localized results. So for example, in cases where very wide decks are being constructed, local concentrations of stresses may arise due to different phenomena, due to different interactions between forces and moments. And in such cases, a line model is not enough to reflect these local phenomena. A point I'd like to make here is that special care must be taken at the interface between solids, shells, and beam elements because they all have different degrees of freedom. Lastly, coming on to meshed finite element modeling. Now, this method of modeling is, of course, one of the most realistic modeling methods, one of the most accurate modeling methods, and it gives the most realistic structural response and provides a very accurate representation of local and global responses as well. And furthermore, in some cases it is also possible to separate the local and global responses. The downside to this is that it is usually quite cumbersome to model an entire bridge using this method. So obviously only certain critical portions are modeled and analyzed. So for example, the anchorage points at where the deck is connected to the cables, or in this case, the saddle clamps of particular cable bridges. Now, before talking about the analysis philosophy, I'll just switch over to our software, Midas Civil, and I will briefly demonstrate to you the basic modeling methodology and the basic modeling tools that are available in our program. So this is our program Midas Civil, and this is the basic bridge. This is the bridge that we shall be modeling today. So we shall be introducing some basic support conditions, the cable elements, and other basic elements as well. So I'll just open up a simple model file, an empty file wherein I have only created my basic material and section properties. Most of these properties are user-defined. They only have the representative properties like the moment of inertia, the shear, the basic areas, and so on, in accordance with the normal spine beam model theory. To quickly model this structure, I shall be using the cable straight bridge wizard. So this wizard allows me to very quickly and very conveniently define the relative positions of my cable stays, the number of cable stays, the various parameters for geometry of my entire cable bridge, and I can update and draw so that I can look at what my cable bridge will look like in the software once it has been modeled based on the parameters entered. So if I just click OK, so this is one side of the bridge that has been quickly modeled for me. I shall now copy this 15 meters laterally, since in this case my deck is to be 15 meters wide. I shall now create the cross members. So here I can choose cross members for the girder. And I can translate these particular members. I can just simply copy them over a particular distance, telling them to intersect the nodes and the elements. So for example, if I want to copy it, say 20 times, so I can do it like so. Say another 15 times. So in this way, I can very quickly and easily create the properties for my cross beams for the deck. Similarly, if I want to create the properties for my pylons, I can do that as well. So just select the relevant properties. And apply. Now, in a lot of cases, it may happen that the feet of the bridge may be slightly spread apart. So even that is quite easy to modify in Midas. All we need to do is just select, for example, let's say I simply move the nodes and the elements follow. So if you don't have perfectly vertical pylons, but instead you have slightly inclined pylons, modification of the model is a very, very easy process. Okay. Lastly, we shall just apply certain boundary conditions. So for example, you can apply fixed boundary conditions like so. And furthermore, to apply the same boundary condition to other nodes, I can just apply it. I can just select the nodes and simply drag and drop from the workspace. So the drag and drop feature, for those of you who have used our program, for those of you who know Midas Civil, you're familiar with the drag and drop feature. For those of you who do not, the drag and drop feature works for even changing section properties. It works even for changing material properties. So this was just a little bit about the basic modeling procedure. I'll now just simply shift over to the analysis philosophy. Okay. Now, for cable stayed bridges, when we first start out with the analysis of such bridges, the first and foremost thing that we wish to find is the value of cable tension that will give optimum deck profile for the final model. Now, the term optimum deck profile will mean different things to different engineers. If you are going by the conventional methods, conventional means, then optimum deck profile will mean the value of cable pretension such that pretension deflections plus dead load deflections will mean zero deflection in the deck. This is the conventional procedure. A more recent, a more modern method is cable pretension values such that we have minimum bending moment profile in the deck. So in that case, we will have a range of values, a range of acceptable values that will need to be used. So regardless, the first and foremost thing that we need to do is find the optimal cable or the final state cable pretension. Next step, we go for a backward construction stage analysis to find the cable forces during erection. This is another very important step because the cable forces that are present during erection time are not the same as the cable forces that are there in the final state. This is because of the deflection of the various segments of the deck and the additional pretension that is caused by the deflection of said segments. Third step, which is which is not really required in case of steel bridges, is the forward analysis, which is mainly used for checking the final pretension values, but is very important for concrete bridges in that it is needed for considering time-dependent effects. And lastly, once all the staging and the pretensioning forces are figured out, we can go with the final checks for seismic, wind, and other effects. So for finding the final cable state forces, we have three basic methods. These are the continuous beam method, the bending moment envelope method, and the influence matrix method. So first up, the continuous beam method is one where the connections between the stay cable and the deck are idealized as pin supports, and linear static analysis is conducted, and whatever reactions that we get from this analysis, we extrapolate them to figure out the cable forces. One of the major advantages of this particular approach is that the creep in the vertical direction is eliminated at the connection locations. Of course, one of the major disadvantages of this method is that sometimes it gives us unrealistic or unachievable creep forces, unachievable cable forces, particularly from the economic standpoint. The next method that I will discuss here is the bending moment envelope method. This method was suggested more recently by Svensson in his book Cable Stayed Bridges, 40 Years of Experience Worldwide. In it, he mentions that continuous beam method may not be the best method for steel deck cable stayed bridges from the economic standpoint, particularly because once we have figured out the cable forces for the dead loads, we then add the live loads and the envelope of bending moment from the live loads. We combine that with the dead load, and whatever final bending moment envelope we get, we conduct design for that. And that is basically what is shown in figure B in this on the slide before you. What Svensson suggests is that we tune the cable forces after getting the final bending moment envelope in figure B such that the final dead load plus live load bending moment envelope is more uniform and as close as minimum as possible across the entire deck. So yes, the tuning of cable forces will mean that the deck profile becomes more economical. However, it will also mean that we may require more cable material because we are providing higher amount of pretension. So in this case, the cost of reduced deck dimensions have to be compared with the additional cost of cable material to know whether this is a truly economic solution or not. Lastly, the influence matrix, or as it is implemented in Midas, the unknown load factor method. Now, this is generally an exception, and this is basically an extension of the unit load method, wherein unit pretension is introduced in the cable elements, and the effect of these unit pretensions is observed on the rest of the structure in the form of an influence matrix. So normally we know from our experience of the unit load method that we can easily get constraints in the form of forces or displacements or moments. But the influence matrix or the unknown load factor method in Midas has also been expanded to incorporate inequalities. So for example, if an engineer wants to constrain the moments in his or her deck section to a particular range, that range of values can also be incorporated, and the program will give you the cable stay force solution for that particular range of values. Finally, talking about cable force tuning. So once the cable forces have been found out, once the idealized cable forces are found out, we would need to tune the cable forces in such a way that the final solution is acceptable to us as engineers. Now, tuning the cable forces is again a very time-consuming process. So in Midas, we have this cable force tuning feature, which allows you to directly see what will be the effect of tuning a particular cable force and what will the effect of that on the rest of the structure. So just before moving on, I'll show you these particular features in our software. So this is a model that already has that is already created. So as you can see, we have unit pretension across all the cable stays. Let me just very quickly analyze this. It takes just about 3 seconds. And now, first and foremost, I will show you the deflected shape under the combination of unit pretension and self-weight. So as you can see, this is the deflected shape that arises due to the self-weight of the girder, the cables, and simple 1 kilonewton pretension in all the cable stays. To find the final state cable forces, we'll use the unknown load factor method. So in the unknown load factor method, we work by the method of constraints. We define certain constraints across our deck. So here in this table, we can see what constraints have been defined. These are the node numbers that represent the node locations of the deck. And I have specified an inequality, and I am basically telling the program that I want to find cable forces such that the overall deflection in my deck is between plus minus 1 centimeter. So these are the inequalities, these are the constraints that we can define. Aside from that, we can obviously also define constraint in the form of reactions, forces, or moments. So we can define, if we want a range of moments in our deck, we can define that as well. So once this is done, we can just go and get the unknown load factors. So we have here, these are the unknown load factors that the program provides us. And in this case, since we have unit pretension, these are the actual pretension forces that we need to use. We can also get the influence matrix directly. So from here, we can see easily what is the influence matrix for this particular model. And we can generate an Excel file that will create an Excel file like so. So this is the Excel file of the influence matrix for this particular model. And it includes the equations. So it is an interactive file. You change any pretension value and the overall displacements will be changed as well. So once this is done, we simply need to make a load combination. Since I have already a load combination pre-made, in this case, I will simply shift to that. And here I can show you what is the deflected shape with the new combination of forces with the factored cable stay forces. So as you can see, the deflected shape is much more uniform now. Once this is done, we may of course want to go for cable force tuning. So you may want to tune the cable forces for a variety of reasons. For example, to make the deflected shape more uniform, or if you simply want to account for the least count of the pretensioning machinery that is there at the field, since it is slightly hard to incorporate decimal points of pretension values at the field. So here, for example, this is the curve of displacement. We can observe curves for bending, for stresses, for moments, for forces, and for basically all the parameters, all the result parameters can have their graphs represented here. Let's say if I change one amount of pretension, so immediately I can observe the effect of that change on the displacement curve. And if I want to see what exactly is the parameter what exactly is the location that is most affected on this graph by this change in pretension, I can simply go to influence values. And with this, I can easily see that changing tension 1 will most adversely affect the mid-span deflections. So I can, if I reduce these, the mid-span deflection will increase. If I increase them, the mid-span deflection will reduce. Similarly, for example, for this case, again, I can increase or decrease the mid-span deflections or deflections at any other location as well. Right. So once the deflections have been found out, once you are satisfied with the overall variation of deflections, with the overall curve that you are getting, you can just either save it as a new load combination, or you can update this to the present model file. And once you update this, what you will have in the pretension values will no longer be unit pretension, but instead they will be the actual pretension values that you got from cable force tuning. So now let me move on with the presentation, and I'll come on to construction staging. Now, in most commercial softwares, construction staging for cable stayed bridges is a two-step process. First and foremost, we do a backward analysis, using which we find out the cable forces during erection. Then we conduct a forward analysis, which is more or less a confirmation modeling, a confirmation action in case of steel bridges, and in case of concrete bridges, it is required for considering the time-dependent effects. Now, in case of Midas Civil, we have implemented a feature which is known as the lack of fit force. So what this lack of fit force means is basically it does exactly the same thing that we wish to find through backward analysis. Lack of fit in terms that the program has been coded is basically the lack of fitting the original shape or the ideal shape that the bridge is supposed to have. So what is the deflection that the model has during construction staging away from the ideal shape? The program calculates this deflection and simultaneously from that deflection extrapolates the amount of force that would be needed to push the segment back to its original position. This directly gives us the actual additional amount of pretension that is required during stay cable erection. Therefore, in summation, if you're using Midas Civil to model and analyze a cable stayed bridge, you don't really need to do a backward analysis. You can simply go ahead with the forward construction stage analysis and use just turn on the lack of fit force option, and automatically the program will account for the additional erection forces during construction, and it will add them to the existing cable forces. Talking a little bit about camber as well, because camber is particularly important in case of cable bridges since they are so sensitive to any and every kind of deflection. Midas is capable of providing both construction as well as manufacture camber. So in case of construction camber, the program can provide camber graphs as well, and the user can also glean the camber values directly from the deflected shape. Furthermore, even manufacturer camber can easily be got through an option which is known as initial tangent displacement for erected structures. Now, before coming on to discuss the nonlinear effects, I'll just briefly discuss with you the procedure for backward construction staging. So of course, in Midas, backward construction staging is also possible. And this is the basic procedure that one goes about for it. So from the final state model, we go on dismantling the bridge in an order reverse to that of the normal construction scheme. And at each and every point, at each and every construction stage, we observe what are the forces in the truss. In this case, what are the forces in the cables? And whatever forces we get just before that cable is removed, those are the forces that are to be implemented at the time of erection, or what one would call as the first stressing. So with this, again, as this is a manual process, and this is a very time-consuming process as well, especially so if a large number of cables are there in your model. So moving on to forward construction staging, I'll show you a slightly different model in this case. This particular model is based on a live project application, and in this particular model, we have about 100 construction stages, starting right from scratch, progressing in the normal forward construction schema, we get to the final stage. Right. So first and foremost, talking about the lack of fit force. So as explained in my PPT, the lack of fit force option is available from the construction stage analysis control, wherein we simply select a group of elements for which the lack of fit force is to be calculated. At each and every point, the program will analyze the structure and observe how much is the deflection of the model during construction staging away from the ideal shape or away from the pre-analysis shape. And based on that deflection, it will get the lack of fit forces. To observe the lack of fit forces separately, we can easily get them from here, from this particular option. And these are the additional lack of fit forces that are required to be input into the cables. So as you can see, these are the additional forces that are needed in the cable. And the program is capable of automatically adding these forces into the construction stage results. Furthermore, talking about camber. So I'll directly show you the camber graphs. So these are the construction and manufacture cambers for these particular for this particular model. So we can easily get the different camber curves for both the construction staging as well as for the final the manufacturing stage. Let me now come on to the last leg of today's web session, that is nonlinear effects. So here I'll talk about the three major nonlinear effects that plague cable state bridges: the sag effects from the cables, P delta effects or second order effects, and large deformation or third order effects. So sag effects from cables can be accounted for in both linear as well as in nonlinear analysis. In terms of linear analysis, it is accounted for by means of the Ernst formula, which I had already shown you, by transforming the by transforming a truss into an equivalent truss element with an equivalent stiffness. In case of geometric nonlinear analysis, cable elements are treated as elastic catenary elements, with their stiffness matrices being changed at each and every iteration of loading. Talking about second order effects or P delta effects. Now, for short to medium span bridges, the deflections can be quite small. So second order effects can be limited to the simply the live load effects. However, for medium or long span bridges, these can become quite significant and therefore need to be considered for both construction as well as final stage calculations, and also for the dead load effect as well. So when we say second order effects in cable bridges, we mean both cables as well as the overall deck sections. Because of the segmental nature of cable stayed bridge construction, the deck the deck usually experiences a high amount of axial force, and because of that, the P delta effect is present even for the decks. Talking about third order effects for very long span bridges. Now, this is usually required for bridges whose spans exceed something like 600 meters or more. In such cases, large deformation analysis may be required, and this is usually done as geometric nonlinear analysis. So in this particular case, Midas provides options for geometric nonlinear analysis as well, for both backward and forward construction staging. So let me show you these options now. I'm sorry. So once again, from the analysis control, here we have the different options for P delta and for nonlinear analysis. So for most bridges, P delta analysis is quite sufficient from short to medium span bridges. So here, if we include the P delta effect, this will consider the P delta effects across the entire construction stage, across the entire sequence of construction staging. For very long span bridges, nonlinear analysis can be implemented, and in this case we have options for independent and accumulative staging. So the independent stage basically is applicable to backward analysis, while accumulative staging is applicable to forward analysis. Here you will notice we can also include the time-dependent effects. So if you have a concrete bridge or a concrete deck structure, so creep and shrinkage would need to be included in that case as well. And lastly, let me give you a very brief comparison between linear static, P delta, and nonlinear analysis, particularly their requirements for cable stayed bridges. In general, there is no hard and fast rule to decide when third order theory should be used for cable stayed bridges. There have been many researches to investigate for potential cutoff points that differentiate between the requirement of P delta and full-blown nonlinear analysis. For short span bridges, for example, Viroglu and others have suggested that dead load distribution can be analyzed just as a first order effect, and second order checks should only be done for live loads. And the same researchers have also specified that for medium span bridges, the P delta effect should be extended to dead loads as well. In case of geometric nonlinear analysis, Wang and others have suggested that for main spans beyond 600 meters, third order theory is recommended. Now, these are just very few researches that I have quoted in my presentation. Of course, other researchers may propose other limits or other values. Engineers may propose other limits or values based on their experience. At the end of the day, it truly boils down to what is the requirement of the engineer based on his or her project. So speaking of projects, I will bring my session to a close by talking a little bit about our project applications. So first and foremost, we have the Ironton-Russell Bridge in this is just crossing the Ohio River in USA. The Weirton-Steubenville Bridge, again crossing the Ohio River, again in the USA. A research undertaken by TU Delft in Netherlands for analysis of a cable-stayed railway bridge. The Korabelny-Fawata Bridge in St. Petersburg with an overall bridge length of 620 meters. The Lazarevsky Bridge in St. Petersburg again, a very elegant looking bridge which utilized Midas Civil. Some record holders now. First and foremost, we have the Incheon Second Bridge, which is the 5th longest cable-stayed bridge in the world today, with an overall bridge length of 1.48 kilometers, main span of 800 meters. The Stonecutters Bridge, which is currently the 3rd longest cable-stayed bridge in the world, with an overall bridge length of 1.6 kilometers and a main span of just over 1 kilometer. And Midas Civil was utilized for construction stage analysis with time-dependent effects, cable tension optimization, geometric nonlinearity, eigenvalue, thermal, and buckling analyses. Lastly, the Sutong Bridge, which is currently the 2nd longest cable-stayed bridge in the world, with an overall length of over 8 kilometers, main span length just 70 meters more than that of Stonecutters, and the types of analyses were also similar to that employed for Stonecutters Bridge. With that, I'd like to bring this web session to a close. Thank you once again for having attended this webinar session. We at Midas hope you enjoyed this session. And now if you have any questions or any queries, please type them out into the questions box and I will be more than happy to answer them.